Welcome back to the course Basics of Mechanical Engineering 2, where we were discussing manufacturing processes. In the last week and in this week, we have discussed machining. In the machining, we have discussed about single point cutting tool, then lathe machining operations, then some of the milling operations, because milling is a very versatile process, very versatile machining system in which we do end mill, we do a lot of kind of the operations that happens on the face, happens inside, cutting slots, etc. Then we also discussed about grinding operations. I will now try to take some problem statements, that is the tutorial session is on the machining, the points that we discussed in the last week and in this week. So, this is tutorial session on machining. I am Dr. Amandeep Singh Oberoi. Just to recall the concepts that we have discussed in the last week about the cutting speed, feed and depth of cut, because generally when we have a specific dimensions of the material, we have a specific machine in which the machining speed is specifically defined. There are variable speeds in the CNC systems. When we talk about, there are machines, for example, if the speed variation is between 0 to 10,000 rotations per minute, we can set even 9992, we can set even 8884 something, the operations even up to the variation of 1 meter per minute speed could be put as an input there. But in the conventional machining setups, the machining speed is sometimes generally fixed. For example, first variation is 100 meters per minute, second could be 120, third could be 140, then it could be 200. So, based upon those only we can have the cutting speed, and feed and depth of cut are also generally fixed accordingly, so that the surface roughness and the kind of the overall machining time is minimum and the quality that you need is appropriate. So, in a lathe machining setup, you can see this is a tool post that is holding the tool and tool is cutting. This is how the chip is coming out, and this is revolutions per minute, that is this rotations RPM, and S is the peripheral speed, it is in meter per minute. So, this is RPM, this is meter per minute that is given here. Now, relative tool travel in one rotation that could also be put as pi into d, that is the whole periphery of the workpiece is taken in one rotation, pi into d. Then peripheral speed correspondingly could be also put as pi d into n. Now, if we have given with the diameter the RPM, that is the rotational speed, we can calculate the speed, the cutting speed or the peripheral speed by pi d n by 1000. This 1000 factor has come because we are converting the diameter into meter, because meter per minute is required and generally diameter is given in millimeters. So, n is your rotational speed, that is revolutions per minute. This is how we get the peripheral speed of workpiece past the cutting tool is equal to cutting speed. Feed, the distance of tool advances for every rotation of workpiece. After each rotation it advances, second rotation it advances. So, after each rotation it is millimeters per revolution. So, millimeter per revolution is also the units of feed. Feed rate, it is linear travel, it is millimeter per minute. This is equal to feed into the RPM. So, this is the feed that is getting into the workpiece, and this is my the initial diameter and final diameter. This becomes my depth of cut. Now, depth of cut that I have given in the next slide, depth of cut is equal to d1 minus d2 by 2, that is this initial diameter minus the final diameter by 2. This is the depth of cut, which is also given in general in millimeters. Now, before embarking upon the problem statements, let us try to see some more relations, because these are important. In this figure that you are looking at, we have the tool when it approaches the workpiece. So, there is a reach of the tool towards the workpiece. When the tool comes very close to the workpiece, the tip has just reached close to the workpiece face here, this distance is known as approach. And after the cutting, the tool also goes over and beyond the workpiece's contact. This is known as over travel. Then the total distance travelled by tool, that is length of single pass. In a single pass, when the tool has to come, there is workpiece, tool has to approach it, this approach length plus workpiece length plus over travel length. So this becomes my total length of pass. This is length of workpiece L plus the total approach, that is X, plus length of over travel, that is Y. Now machining feed is cutting speed times feed per tooth times the number of teeth, and length travelled by the tool in N1 pass is total distance travelled by the tool in the single pass into the number of passes, that is N1 number pass. So if in question length of the tool approach and length of the tool over travels not mentioned, then neglect, then X and Y is neglected and length of the single pass is equal to the length of the workpiece. Then machining time would also have to be calculated sometimes. Machining time or cutting time, that is the time required to machine one pass, is job or length of workpiece in millimeters, that is this time is equal to L by F into N, where L is our length of workpiece, F is my feed and N is the rotations per minute. F feed is in millimeter per revolution, feed per tooth, that FT is in millimeter per tooth, FR is in millimeter per minute, and rotation N is in RPM, outer diameter D naught, cutting speed is V, that is in millimeter per minute. So this could also be put as L by FR, that is L into pi into D naught by F into V. This is time in minutes. Manufacturing time is the overall time to produce the product, is machining time plus setup time plus moving time plus fitting time. That is a different scenario. We are only trying to talk about the machining time majorly here. Then we sometimes have to calculate the material removal rate. Material removal rate is in three forms, that is material removed in one revolution, then n revolutions per minute, then depending upon the width of the tool, depending upon depth of cut, also this is calculated. First is material removal rate per revolution, which is equal to pi d into d into f. This is diameter of workpiece, this is depth of cut, and this is feed per revolution. So this becomes millimeter into millimeter into millimeter per revolution. So that becomes millimeter cube per revolution. That is volume removed per revolution. Job makes n revolutions per minute, then it becomes pi d f into n, that is d is in millimeters, depth of cut is also in millimeters, this feed is in millimeters per revolution, and n is revolutions per minute. So this becomes the volume removed per minute. If width of tool, depth of cut, machining, feed in millimeter per minute are given, then it becomes W into D into Fm, which is W in millimeters, depth in millimeters, and Fm in is millimeters per minute. So this turns to be millimeter cube per minute. Let me now come to a problem statement, a very simple problem statement where feed rate of a single point cutting tool is 3 millimeters per revolution and the workpiece is rotating at 600 RPM. Determine the total machining time to turn the cylindrical surface of length 300 millimeters of the workpiece. So here we have been given 3 millimeters per revolution, that is my F is equal to 3 millimeters per revolution, and I have been given RPM, that is 600 RPM, that is N, it is the rotational speed of the workpiece, and also it is given the length of the workpiece. L is equal to 300 millimeters. I have to calculate the machining time. Just to recall the machining time, it is L by F into N. Simply the first relation would give you the solution. So time T is equal to length by feed into the rotational speed. This is equal to 300 by 3 into 600, that is equal to 0.1666 minutes. Remember that this is in minutes. If you wish to convert this into seconds, so 0.1666 minutes is equal to 0.1666 into 60 seconds, that is equal to 10 seconds. This is a very simple problem. Similarly, there is another problem in the same direction. A 150 millimeter long and 12.5 millimeter diameter stainless steel rod is being reduced to a diameter of 12 millimeter by turning operation. The initial dia and the final dia is given. Initial dia here is 12.5 millimeters. Final dia here is 12 millimeters, and length is also given 150 millimeters. The lathe spindle rotates at 400 rpm. We have been given the rotational speed 400 rpm. The initial dia D1, the final dia D2. And we have the length of the workpiece as 150 millimeters. Simply to calculate the cutting speed, V is equal to pi dn. Here d is the initial diameter only. This is equal to pi times d, that is 12.5 times the rotational speed, that is 400. Here, because this is given in millimeters, I have to also divide it by 1000. So this by 1000, this gives me V as 15.7 meters per minute. Because I divided by 1000, I have converted the units to meters per minute, and the diameter was given in millimeters. So D2 is not required here. Anyway, it was given in the question or problem statement. Another problem statement tells that on a lathe, a cylindrical workpiece of 100 millimeter is being turned. The RPM is 100. Find the cutting speed. Simply, you can calculate the cutting speed here using the formula V is equal to pi dn by 1000. You can calculate it by yourself. I'll just give you a solution. The solution will give you V is equal to 31.41 meters per minute. A better problem statement that I'll try to solve here, where it says a hollow workpiece of 250 millimeter long and 40 millimeter diameter is to be turned in 4 passes. The number of passes are here. Calculate the machining time if the approach length is 15 millimeter, over travel is 10 millimeter, feed is 0.7 millimeters per revolution, and cutting speed is 32 meters per minute. This is a good problem where we have workpiece and we have approach length and over travel as well. Just to recall, the total distance traveled, total distance is equal to length of the workpiece plus the approach length plus the over travel length. Here we have been given length of workpiece as 250 millimeters, the approach length as 15 millimeters, and over travel as 10 millimeters. So this gives me the total length, it is length of single pass is equal to 250 plus 15 plus 10, LS is 275 millimeters. This now gets into the calculations. Also have been given the other parameters here, such as we have been given diameter is 40 millimeters, feed as 0.7 millimeters per revolution, speed as 32 meters per minute, and number of passes are given as 4 passes. Now let us first try to find the value of n, because the question is machining time, and we know to calculate time we have to put the formula time is equal to length by feed into the RPM, that is the total length here. Now the total length traveled by tool, total length traveled in 4 passes is equal to 275 into 4 is equal to 1100 millimeters. And to calculate n, we know that speed is equal to pi d n by 1000, therefore n is equal to 1000 into the cutting speed, that is 32 by pi into the diameter, that is 40. This gives me n is equal to 255 RPM. To calculate the time, I will just put the values here. This is equal to the total length traveled, that is 1100, by feed, it is 0.7, into the calculated RPM 255. This gives me the machining time, that is Tm, as 6.16 minutes. There is a similar problem statement where we need to find the machining time. To find the machining time, sometimes a feed is given, speed is given, and like we have seen the approach length, the over travel length, those are given. In this problem statement, we have to calculate the machining time. That will require to finish a vertical flat surface of length 120 millimeter and depth 15 millimeter by an 8 teeth HSS end mill. This is a problem in milling operation. Now here an important factor is we have got number of teeth as well, and here we are also being given with feed as 0.15 millimeter per tooth, and number of teeth are also given. Let us see how do we calculate this. A cutter of 32 millimeter diameter in a milling machine, cutting velocity is 30 meters per minute. Now here L is equal to 120 millimeters, D is equal to 15 millimeters, N is equal to 8, D, that is the diameter is 32 millimeters, the speed is 30 meters per minute, and feed per tooth Ft is given as 0.15 millimeters per tooth. How do we calculate this? We will find n, then we will put that value of n to find the machining feed, that is machining feed is equal to feed per tooth into the rotations per minute into the number of teeth. You will find machine feed. This is machine feed. Then cutting time could be calculated. Cutting time, that is T is equal to L by the machine feed. This you will calculate. How do we find good N? Simply you will use the relation V is equal to pi d N by 1000. Just calculate this. The cutting time that you will find in the end, this will come as 20.1 seconds. This is for you to calculate here. Another problem statement in milling, where it has been given a slab milling operation is being carried out on a 50 millimeter long and 10 millimeter wide high strength block at a feed of 0.1 millimeter per tooth. So, let us see what we have been given. Length is equal to 50 millimeters. We have also been given width as 10 millimeters and feed per tooth Ft is equal to 0.01 millimeters per tooth. Depth of cut is 0.15 millimeters. Small d, that is depth of cut, is 0.15 millimeters. The cutter has diameter of 3 millimeter and has 10 straight cutting and rotates at 150 rpm. So, this is 10 straight cutting teeth here. Cutter dia is 3 millimeters, number of teeth are 10 and rotation speed, that is rpm, n is equal to 150 rpm. Calculate the MRR and cutting time. To calculate the MRR, let us first try to find the machine feed. Machine feed, this is equal to the feed per tooth into the rotations per minute into the number of teeth. This is equal to 0.01 into 150 into 10, this is 15 millimeters per minute. Then MRR, that is material removal rate, could be calculated from the relation W into D into the machine feed. So, width is 10 millimeters, depth of cut is 0.15 and machining feed is 15. This gives me the value of MRR as 22.5 millimeters cube per minute. Cutting time, T is equal to length by the machine feed. This is equal to 50 by 15 into 60, because I am converting this into seconds. This is equal to 200 seconds. So, this is the MRR and cutting time. Next is the concept of taper turning. Taper turning means on one side diameter is larger, other side the diameter is smaller. The D1 is a larger diameter, D2 is a smaller diameter, and there is a length that has been turned from the larger to the smaller diameter. And here we have multiple parameters. Here we have taper angle alpha, here we have conicity K. By the definition, taper turning is a machining process used to gradually reduce the diameter of a cylindrical workpiece over a specific length. A taper is defined by the difference in the diameters along the length of the taper. So, here this alpha is half of this angle, total angle. In conicity is also calculated. How is K calculated? Let us see here. K is D1 minus D2 by L, that is conicity. D1 is a larger diameter, D2 is a smaller diameter, and L is the length of the taper. We can also calculate the taper angle, that is tan alpha is equal to d1 minus d2 by 2L. If you see this triangle here, so here we can develop a triangle here. This is one triangle and that triangle. From using this triangular relationship, tan alpha is d1 minus d2 by 2L, that is conicity by 2. This concept is widely used in manufacturing to produce machine components such as shafts, spindles, tool holders, etc. Let me try to see a problem statement where a cylindrical workpiece is being taper turned over a length of 400 millimeters with a larger diameter of 100 millimeter and smaller diameter of 60 millimeter. We have to find the taper angle and conicity. So, this is a problem that is given. We have been given L as 100 millimeters, the larger diameter D1 as 100 millimeters, D2 as 60 millimeters. Taper angle is to be found, alpha is to be found, and we have to find the conicity. So, we know conicity that is K is equal to D1 minus D2 by L, that is 100 minus 60 by the length of the workpiece. This is equal to 0.1. This is a dimensionless quantity. Right? Then tan alpha is equal to conicity by 2, or it is d1 minus d2 by 2L. So, we get alpha is equal to tan inverse of 0.1 by 2, that is equal to tan inverse of 0.05. This gives me alpha is equal to 2.86 degrees. This is my taper angle, this is my conicity. With this, I am taking a break here, and the second part of the tutorial would cover the other problems. This was just a simple machining systems. Now, we will also try to see the tool, the shear angle, the nose radius of tool, how do we calculate those? Also, the tool life, that equation that you saw in the theory lectures, that also would be covered in the next part of the tutorial. Thank you.